Okay, so this is Math313, number theory. This is lecture 14. So we're going to be doing stuff on the Euler Totient function. One of the nice things about having a textbook for the class is I don't have to do every proof that's in the book, and I also don't have to prove things the same way as they're in the book. This doesn't mean that the way I'm doing is better. It is, but it doesn't necessarily mean that. It just means it's a different perspective, and it's often useful to see different ways of looking at the same problem. So I will do the first proof in the spirit of the book on the Euler Totient function. So theorem. If m and n are relatively prime, then phi of mn is phi of m, phi of n. So this means that phi is a multiplicative function. This is an extremely valuable result. What it means is that we only need to understand phi at primes and prime powers. And from that, we can understand it everywhere. As an immediate corollary, since phi of p to the k is p to the k minus p to the k minus 1, which is p to the k 1 minus 1 over p, we get phi of p1 to the k1 pr to the kr is just n 1 minus 1 over p1 dot 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 1 minus 1 over pk. So this is the power. So if you were actually going to compute things, you would actually just form tables of primes and prime powers, or maybe even not even prime powers, because we can immediately get things by just knowing how many times the prime goes in. So the question is, how do we prove this? So I will go through the book's proof, which is basically a nice counting argument. I will just mention as an aside, remember that phi of n is the cardinality of z mod and z star. And this is the number of x such that 1 less than equal to x less than equal to n, and xn equals 1. And we've seen that these groups are extremely important in number theory. OK, so the way we're going to do this is we're going to consider two sets. So proof. So we're going to have the sets A and B. Hello? And so I always want to make sure I do this the right way. OK, so A is going to be A1, A2, A phi m. And B is going to be B1, B2, B phi n. So the question is, which elements do you think we're choosing for A? Which elements do you think we're choosing for B? Now, what's nice about A times B in terms of size? So what would the size of A times B be? Yeah, it would be phi m times phi n. So we're going to try to count something two different ways. So the product of these two has the right size. What elements do you think we might be choosing for A? I'm taking phi of m elements. Yeah, this is probably the elements of z mod mz star. And this would probably be z mod nz star. When you think of what's a natural set of phi m numbers, what's a natural set of phi n numbers, these are the natural sets. And I'll choose them so that they're between 1 and n minus 1, 1 and n minus 1. And now I want to look at linear combinations. So consider all numbers of the form, let's do it, an plus bm, where A is in A, B is in B. So when you look at something like this, these are fixed. We're given n and m. and these are free. Oops. So B and A are free. So how many elements do we have in this set? So we have I'm sorry? We don't have nm elements. How many choices for A do we have? We have phi of m choices for A. We have phi of n choices for B. We have phi m, phi n elements. Right? The hope is that these are all distinct mod what? Yeah, hope distinct mod mn. Because if they're distinct mod mn, then this is in some sense a set of representatives. Well, maybe not. We don't know yet how many representatives, how many different residues there are. We hope that this will be. We expect this to be. But we don't know yet for certainty. But if there's repeats among them, we know that's bad. So the hope is that this will be everything. So imagine, double G. Imagine an plus bm. Do you like tildes or do you like primes? Tildes, all right, is a tilde n plus b tilde m mod mn. So imagine you had two numbers that were the same mod mn. I personally like tildes a little bit more, but the primes is a little bit nicer in terms of spacing. Tildes is more fun though to write. All right, so we have two things that are equal, and we want to somehow get a contradiction. How should we approach an algebra equation like this? So we know m and n are relatively prime. Yes. Yeah, get the ends. Years ago when you had 3x plus 2 equals 4x minus 8, you would bring all the x's on one side and all the constants on the other, and you would solve it. We're doing the same thing here. Put all the n's together, so we'll have a minus a tilde times n equals b tilde minus b times m mod mn. Now we use the fact that m and n are relatively prime. So this is a multiple of mn. Can m divide anything in n? No. N and m are relatively prime. So the only way this could be 0 do I want to do it this way? All right, so what we're saying is they differ. Well, do I want to do it this way? So this is a natural thing to try. So what I wanted to do is I wanted to say that this would have to be 0, this would have to be multiple of m, this would have to be multiple of n. We know that they're equal mod mn, so that they differ by some multiple. So what I could do is I could say this is equal to plus some multiple of mn. Right? Well, I know m divides this side. So this is a multiple of m. And since m has nothing in common with n, every prime that divides m must divide a minus a tilde. And it must divide to the same power. So this must be a multiple of m. So I couldn't just immediately say this, but if I say that there's a multiple k here, this then works. So this has to be a multiple of m. What's the only way this can be a multiple of m? It's got to be 0. Because a and a tilde go between 1 and m. And we know it's not going to be m. Well, if it was m and 1, that difference would be m minus 1. It would not be a multiple. So the only way it can work is if a equals a tilde. We're happy that a equals a tilde. Do I have to go through the proof to say b equals b tilde? No. It's completely symmetric in m and n. It's completely symmetric in a and b. I could have done the whole argument from the other perspective. And so we similarly get b equals b tilde. And again, we could have just gone that by looking at multiples of n. So what this means is if two of these numbers are the same, then they must have been the same. They must have had the same a and the same b, so they're distinct. So we're halfway there. Okay, any questions on this part? We all good? Okay, so we've shown that this is a set of distinct residue classes. So what's the only thing that could prevent this from being a full proof?
If there are more than the ones we counted?
Yeah. So how could there be something else? How could there be something new? So these are all distinct mod mn. So what could we have missed? So what are your thoughts? What could we be missing? How could we try to find it?
So something that's relatively prime to mn
Okay.
can't be made with something in a times n plus something in b times n.
So is there an x such that there do not exist a in a, b in b, with x equals a n plus bm? So how do we try to find something like this? Now, are there any x that are not of this form a n plus bm?
What if we assume there is and then show that there can't be?
Okay. Well, I'm saying, do you think that there are any x that are not of this form? And if so, what's true about such x? So there's nm numbers. Do we expect all the nm numbers are of this form? So it's not just an x. This is a very special type of x. What must be true about this x?
Less than mn.
Well, it's less than mn, but I need more than just less than mn. Because we have mn numbers. How many numbers do we have in this set? Phi. That's much less than mn. So there should be a lot of x that aren't of this form. Which x do I care about? I don't care about a generic x. I care about an x with a certain property. Relatively prime. Is there an x such that there's no a in a, and we need x and mn equals 1? Right? We're not trying to do this for an arbitrary x. We're trying to do it for an arbitrary x in z mod n z, z mod m n z star. For an x that's relatively prime. Those are the only ones we need to look at. So how might you try to approach this? So we can try to do a proof by contradiction. We can try to do an existence proof, a constructive proof. You know, the book has a proof, which hopefully you've read. But if not, we can try to do it another way. What theorems do we have that might be useful? Do we have any theorems that could help us solve congruences? So we have Chinese remainder. Maybe that could be useful. This is not in the book. You know, this is trying to do a different proof right now on the spot. Let's see if we can make it work. So Chinese remainder. So let's say we have some x relatively prime to mn. So we know x mod m equals something. What should we call that? I want good notation. Could call it y, but we're also going to then look at x mod n, right? I might put like a subscript m here and a subscript n to just say I'm taking its mod m, I'm taking this mod n. And because these are relatively prime, there is a solution, right? Well, it's not too surprising. We're starting off with an x that's relatively prime to mn. So the fact that there's a number that simultaneously solves these is not too surprising. But the Chinese remainder tells us how to find it. Solution. So what is the solution? What does the Chinese remainder theorem tell us?
Something times the inverse times xn plus something times the inverse times xn.
So okay, so it was something times m, something times n. Right? We're trying to build something up. So let's say we have n here. Was the Chinese remainder theorem something like this, where we had a coefficient in front of n and a coefficient in front of m?
You want one to cancel when you're doing this.
Yeah. So when I look at things mod m, this is going to vanish. So what I could look at is look at n mod m inverse and put a x m here. So, you know, again, this is different notation than we had in the book, but I really like this notation because it highlights what's going on. I take the inverse of n mod m. So nm inverse times n is congruent to 1 mod m. And now if I look at this mod m, well, if I look at this mod m, this is going to just be 0. nm inverse times n mod m is going to just be 1, and then I'll just get xm. You know, it's not going to be a big surprise over here. I'll put m sub m inverse and an xn. And now when I look at things mod n, that will vanish. So I've now written my x as a combination of a multiple of n and a multiple of m. All we have to do is show that this is in A and this is in B. So we need xm nm inverse in A, and we need xn mn inverse in B. Well, A is the set of all things that are relatively prime to M. Since n is invertible mod M, and it's invertible because it's relatively prime, we have to justify why does this exist. It exists as n and m are relatively prime. So we can now use the Euclidean algorithm. So if you're relatively prime, you're invertible. So this nm inverse exists. This exists. So that's the only thing we have to be careful about. Is xm relatively prime to m? If so, we win, right? All we need now is that little xm to be relatively prime to m. Is xm relatively prime to m? Okay, I see you. So why is it relatively prime?
Because all factors of m are also factors of n.
Yeah, basically, we've said x is relatively prime to m times n, so I can just put my hand here. It's relatively prime to n. So this actually gives us a constructive proof of you give me an x, which thing in A do I take, which thing in B do I take. So nm inverse exists as mn equals 1. xm is in A as x mn equals 1. And that finishes the proof. So with two finite sets, if you can put them into a one-to-one correspondence, they must have the same number of elements. Right? So if everybody were to take off their left sneaker and pass that forward, that should be a one-to-one correspondence. I think everybody's wearing sneakers, or generalized sneakers, also known as boots, shoes, stuff like that. There's a one-to-one correspondence. So here, I've shown you give me any x, I can find something in my set that works. So everything is hit. And nothing is hit twice because these are all distinct. So they must have the same cardinality. Technically, it wasn't your phone ringing, but it's...
We'll talk.
We'll talk. OK, so any questions about this? And again, there's another proof in the book. It's worth looking at that. I did the first part the same way the book did. This is why I was checking to make sure I didn't go off on a tangent for that. But I wanted to show you the Chinese remainder theorem. This is a result we did, and you can always ask the who gives a shit question. Why did we spend time proving something like the Chinese remainder theorem? It's really useful for stuff like this, and it gives us a constructive way of finding things. So now we know phi mn is phi m phi n, and we had that nice corollary counting things. Okay. Any questions on the proof? So it is really worth looking this over. There's a lot of good ideas in this proof. Okay. So now we've stated the corollary, and then I'm going to switch things up. We'll talk about average order in a second. The book has two nice results, and the book proves them, but I want to give a different proof. I'll give the same proof for the second part. So theorem, phi of n is the sum d divides n of phi of d, and making sure I'm doing this right. Oh, I'm sorry, this is n, sorry. That looks long. And then phi of n is the sum d divides n. In the book, there's two different ways to write it. They want to write it this way. Mu of d n over d. OK. Do these two statements remind you of anything we saw in last class? What result?
What was when we were doing the arithmetic convolution?
Yeah, it's when we're doing the arithmetic convolutions or the Dirichlet convolutions. So this is like, we have Dirichlet convolutions, and we have the Mobius inversion formula. So the second claim immediately follows from the first with the Mobius inversion formula. And if you prove this one first, you should be able to get that one also by using the Mobius inversion formula and just using Dirichlet convolutions. So really, it's sufficient to just prove the first result. And the book gives a nice proof. You know, I have nothing against that proof. If you want to do things like number theory, it is a good way of building your familiarity with manipulating sums. And a good chunk of your life is spent manipulating sums. But there's another way to do it, and it's a way that I think highlights a lot of what's going on. And it highlights a general proof technique. Most of you, I'm still pretty sure, are not planning on becoming professional number theorists. That's fine. So most of you are probably not going to use these specific results for the rest of your life. This is why I don't want to just prove these results quickly and move on to more results. This is not the purpose of this class. It's not to throw in as much number theory as possible. If you do want to become a professional number theorist, if you are thinking about that, please let me know. I'd be very happy to talk to you. I think it's a nice life. But I really want to emphasize the thought process. How might we prove statement number 1? So prove that n is the sum of d divides n of phi of d. Or do you even think that the statement is true? Possible I copied it wrong on my notes and copied it wrong when I went on the board. I did double check. I really did look at the paper again to make sure I wrote it right. What do you do when you see a statement like this? What's your first thought? First thought when you see something like this, what should you do? Try?
Just try a couple.
Yeah, try a couple. What do you think the first n we should try?
1.
Yeah. So n equals 1. Then we have the sum d divides 1 of phi of d. Well, that's just phi of 1. And that's just 1. OK. Beautifully successful. What should we try next?
2.
We could try 2. Or more generally, rather than just trying 2. And again, it's not wrong to try 2. But we could try a whole class of things altogether. Yeah, let's try primes. So if n equals a prime, then we have the sum d divides p of phi of d. It's going to be phi of 1 plus phi of p. And that's going to be 1 plus p minus 1 is p. And I'll put the parentheses there. It may not be clear, but this is a really nice kind of sum. Anybody know what kind of sum this is? May not be clear from just writing it like this. But this is a very famous type of sum. OK, let's look at another case. What should we look at next? So that's one question. Should we do product of 2 distinct primes? What else could we do?
The same prime.
The same prime twice. Now, most of the time, I've always told you which is the one you should do next. Same prime, because these are multiplicative functions. If you understand what's going on at a prime, prime powers, you've completely understood that prime. And then you can break things up into different primes and see how they combine. It's not wrong to go to 2 distinct primes, but I would probably do n equals p squared first. Right. So we get phi of 1 plus phi of p plus phi of p squared. And I'm trying to write it in a very illuminating way. So what's phi of 1? What's phi of p? What's phi of p squared? We have two ways of saying what phi of p squared is. One way is helpful, one way is not.
Is it A times phi of P?
I'm sorry? So you could do it as p times phi of p,
Or p times p minus 1.
p times p minus 1. There's another way of doing it.
P squared minus p.
P squared minus p. So the p squared minus p is the better way of doing it. And what I will do is I'm going to shift this 1 over and write it as 1 minus 0. Now you can see the 1 and the negative 1 cancel. The p and the negative p cancel, and you're left with the p squared. So I think it's now clear what's going on if we had p squared. If we had p cubed, we would just have a telescoping sum. So you might have seen telescoping sums in calculus when you did the fundamental theorem of calculus, that the area under the curve is the antiderivative at b minus the antiderivative at a. You might have been using the mean value theorem, and you have all these things and they cancel out. Does this vaguely sound familiar? Or can you at least nod your head and humor me? Okay, thank you. That was a good nod. Thank you. Okay. So the proof is actually very nice now. If n is p to the k, then the sum of d divides p to the k of phi of d is going to be 1. I'll do it this way. Phi of 1 plus phi of p plus phi of p to the k. This is going to be 1 minus 0 plus p minus 1 plus p squared minus p plus dot 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 plus p to the k minus p to the k minus 1. And you see everything just cancels, and you get p to the k. This is what I like about this proof, is it really shows you what's going on with the sum, and you get a flavor of what's happening. Okay, now we have to decide where do we want to go now. We've completely understood p to the k.
Two distinct primes.
So now let's go to two distinct primes. We could, of course, go directly to p to the k, q to the l, but I think it's better to just do two distinct primes, really build up the intuition and see how you attack problems like this. Okay. So telescoping sums are wonderful. If you can recognize something like this, it's a great way. So now n is pq, and we now want to look at the sum d divides pq of phi of d. This will be phi of 1 plus phi of p plus phi of q plus phi of pq. Right? 1 plus p minus 1 plus q minus 1 plus p minus 1 q minus 1. Doesn't look so clear now. Any thoughts as to how we should combine?
You maybe group and then
But what do I group?
so the 1 times p minus 1 and q minus 1 times p minus 1 and then
So I want to group what? 1 and...
You could do, yeah, q minus 1 plus 1 times p minus 1. Simplify it a little bit.
So you want to combine these two?
Sure.
All right, so if we do this algebraically, if I combine these two, I will get p times q minus 1 I could combine these two, right, and get a P. Then I could pull out the P and get a Q. Do you have an idea of how to do it now if I gave you PQR or if I gave you P squared Q cubed? Again, I don't care about this result. I probably shouldn't be admitting this so often. I really care about the thought process. How should we attack this? Do you see a way to generalize this? Too often we present mathematics to you as this completed subject, fully formed. Here's the definitions, here's the axioms, here's the theorem, here's the proof. Boom, 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 boom. Complete logical progression with nothing to chance. How do you come up with the arguments? So I'm saying, I'm happy to do either PQR, P squared Q, P squared Q squared. What do you want me to do next? Do you see a way to extract something from this that allow you to handle things in general?
We see PQR.
We can try PQR. So let's say n is PQR. So we now want the sum of D divides PQR of phi of D. So this is going to be phi of 1 plus phi of P plus phi of Q plus phi of R plus phi of PQ. Just trying to make sure it's going to all be in focus. Plus phi of PR plus phi of QR plus phi of PQR. 1 plus P minus 1 plus Q minus 1 plus R minus 1 plus P minus 1 Q minus 1 plus P minus 1, my arm is getting tired, R minus 1 plus Q minus 1, R minus 1 plus P minus 1, Q minus 1, R minus 1. I think it's still just barely in focus. All right, what do we do now?
Do the same thing.
All right, so how do we start doing it?
Group the last two terms.
All right, so we want to group these two?
Uh,
So this would then become P times Q minus 1, R minus 1?
yes.
Okay, so we could try doing this. And this would become P times Q minus 1, R minus 1. Now what? Well, maybe if I group these two together, I've got a Q minus 1, a P minus 1, and a P. That would give me a P times Q minus 1. Yes?
So like the last term, the -1,
Yes?
we multiply that all out and then like subtract. Or if we multiply that out, are we left with PQR plus or minus the rest of the terms?
We have to be. Because it ends up as PQR, right? So if we multiply it all out, it's got to equal everything else, right? So that's a good observation. So then you would just need to show that if you multiply this all out, you clearly have a PQR piece. Now you would have, take the -1 and take the other 2, so that would cancel. And then you could have 2 -1s, which would then become a +1 with an R minus 1. So is that now reinforcing? And we're going to end up with a -1 at the end, which will cancel with a +1. So we could try to do all this algebra like this. And it is possibly a way to make this work. I'm just hoping that at this point it seems like this is not the clearest way to approach it. Let's go back to what we had a while ago. The reason it worked so nicely in what we had before was we had a telescoping series. Telescoping sums are extremely nice. So the question is, can we somehow get another telescoping sum? Okay. So now if we go back to this, this was the method that worked. But let's look at 1 plus phi of p times 1 plus phi of q. If we multiply this out, what do we get? We get our expression. Right? This is what we would have had if we just had p. This is what we would have had if we had q. Let's just put them together and multiply. If you multiply them out, 1, phi of p, phi of q, phi of pq. And this is just p, this is just q. If we had three things, if we had p, q, r, which is what we're doing over here, what we can view this as is this is the same as 1 plus phi of p, 1 plus phi of q, 1 plus phi of r. For each one, we can look at it as either we have d includes p as a factor or it doesn't. And when we multiply this all out, we'll get our answer. And then this is just p, q, r. So the idea is to use the telescoping series for each one. So in general, if I give you n is p1 to the r1, pk to the rk, we'll have a sum d divides p1 to the r1, pk to the rk of phi of d. And I claim this is just going to be 1 plus phi of p1 plus phi of p1 to the r1. Because for d, I've got to have some power of that first prime. And the whole thing is it's multiplicative. And then I would just multiply it by all the other pieces. And then we've already shown what this one is. This is just a telescoping series. This is just p1 to the r1, pk to the rk. And that finishes the proof. So it's really, what is the best way to get to it? So your idea of saying, well, look, if we expand out the last thing, it's got to be what we want minus everything else. Can you just show that things cancel in a nice way? What's really going on is that we have a multiplicative function. And so all I need to do is for each d, I can write d as p1 to the l1 dot dot dot, pk to the lk. So phi of d is phi of p1 to the l1 dot dot dot, phi of pk to the lk. That's what each piece is looking like. So it really factors like this. And if I view it as a factorization problem, I've now reduced it to a bunch of simpler problems that I understand. So the hardest part in all of these problems is finding the right perspective. So we've talked a little bit about the prime number theorem. This is one of the big results in mathematics. The very first conference I went to was the 100th birthday party of the prime number theorem. I had just graduated from college. I was able to get some funding to go to Seattle for a conference. And one of the speakers was Atle Selberg, who is one of two people to have done something that we did not think could have been done. So when the prime number theorem was first proved, it used complex analysis. And this just infuriated a lot of mathematicians. We're counting integers. We're counting primes. Why is the square root of -1 coming into play? This doesn't mean that they're upset that this is a proof. Complex analysis is a very powerful subject. Not surprisingly, if we use complex analysis, we can do a lot of good things. But one would think that for a simple counting problem, we shouldn't have to go to the complex plane. There's a great line, the shortest distance between two results in real analysis is through the complex plane, or something along these lines. We'll be teaching complex analysis here next fall, I believe. Strongly recommend if you want to do graduate school in mathematics, you take complex analysis. It is incredible the results you have in that subject, the power of those results. But it was infuriating. And so people thought there's probably an elementary proof of the prime number theorem, just like we had an elementary proof of the infinitude of primes. But no one could find one. So eventually people conjectured two things. No elementary proof exists, or if an elementary proof exists, then it's going to really illuminate the subject. Both conjectures are false. There is an elementary proof, and it really does not give us any idea of what's going on. But I can give you an elementary proof of the prime number theorem just using logarithms and countings and additions. It's extremely clever how you combine these things. And unfortunately, there was a little bit of a controversy between how Paul Erdős and Atle Selberg worked together on the proof of this. I will post a nice article by Dorian Goldfeld on this. This is one of the few times where you have mathematicians fighting each other. And there is an elementary proof. But that doesn't mean I get much from reading it. That doesn't mean I have an idea of how to do it myself. That's why I really want to spend the time and take a lesson to really go through a result like this. How should we think about this? Because at the end of the day, this looks obvious. Oh, yeah. We just use the multiplicativity and we just multiply it out. It factors like this. We should have seen the factoring earlier. How should we find the good way to combine things? The danger of looking at small cases and being misled as to what's the right way to combine. Because, again, we're going to get the right answer. So however you combine, you will get the right answer. But you may not get the right answer in a way that generalizes. Okay, so this is probably a good place to stop. We will continue with Chapter 5 on Monday, but we'll also probably jump into maybe a little bit of Chapter 6 on pi, because it will be essentially the closest to Pi Day possible for us.